Hi everyone, I am Sai Prakash from Qualcomm Bangalore. So I mostly deal with debug features which are both Qualcomm internal as well as upstream as well. So tracing is not new to me. I started my career with tracing. So basically 3 years back in Sony, there was something called as first challenge there, for the new joinees, and they would give us 3 months and just tell, okay, do something with the kernel. So the first project was something called as early kernel debugger. So basically that's an Ftrace alternative. So basically we created one more, a similar kind of Ftrace thing where we use a different GCC compiler flag called as finstrument functions. I'm not sure how many of you know it, but yeah, basically for Ftrace currently we use something called as -PG option. So for instrumenting the functions. So it's something similar to that. So yeah, so I'm interested in tracing and other debug, exploring other debug options. So let's start with this event tracing and Pstore. So let me go over the overview. Yeah. So you don't need to go over this one because I'll just explain you. We had 3 requirements. So one was how do we trace all the register reads and writes. So what interface did we have? Downstream, it's a different way followed. So I'm going to explain what was followed downstream in Qualcomm, and then what we have in upstream already. So what we can use. So that is one thing. And where do we store the logs? So currently how it's done in downstream, it's via randoms. I'll be explaining that. And then upstream, what other facilities do we have? Then third main requirement is filtering. So that was something, again, the downstream follows a different approach. So something upstream, we already have a very good interface for that. So I'm going to tell you guys what we used for upstream as well. So after that, I have some 2-3 ideas. So for upstream kernel. So yeah, so it all started with something called as RTB. If you are in Qualcomm, I think you will know. But for whom it's new, it's called something as register trace buffer. It was originally developed by Laura when she was in Qualcomm. So and it was developed like a long time back, like 8 years ago. And in Qualcomm we still use it. So it's quite a powerful debug feature, I would say, because every time there is a crash or any watchdog bytes, stability team would come and ask, okay, where is RTB for us? So that is something. What is RTB? So basically, to explain it in a simple the basic use case is to debug the abnormal resets. So you have a watchdog byte or you have some unclocked access, and the system goes boom. And how do you how do you debug that? So they provided with a simple interface where you would store those events in uncached buffer, and later on, as a part of randoms, you collect the randoms and you basically extract the events. So mainly it is for storing events in the uncached buffer. And the main thing is here is the last few events. So last few events that are actually logged are very important in our case. And they are logged per core. So you'll know exactly on which core what was the last register access. And the main thing I've used is it's useful in the investigation. So it's not like exactly it will give you the actual root cause. So it is just one of the debug mechanisms which are available for us. So that was what RTB was providing us downstream. So if you are interested, there is a link over there for RTB on MSM kernels. So this is an example of how an RTB log look. So if you look at the last line, so that is a sample program which I wrote, and I just took from the technical reference manual some secure register, and on reading those register, you will go, your board will go, board will just crash up. So this is on SDM845 MTP test platform. So I would read some secure register and it would go, the target would crash. So how the RTB would work in such case? It would log all the events, all the events per core. And this is just from one core I've taken, for example. Like let's say this is, I think it's from CPU 3. So these, you can see here, these are the log types. So there are RTB provides again facilities for different log types. It's not just register reads and writes. So it will actually help in getting to know, IRQ, context IDs. So these are the different log types which are already available in RTB, and we can add even more if you have any ideas. So basically, I'll be focusing more on register reads and writes. So this is the one, this is the last event which was logged in that uncached buffer, and actually it clearly points, to the actual exact function and the offset within that function where the register was being read. So if you see this, this is the register being accessed, and there are several fields here. So main thing is this one, timestamp, which we need to take care of, and this is the log type, and this is the caller function. So if you see there, so that is a readle function where the MTP is going to get crashed. So it's kind of easier to debug this way. It's not always like this. I mean, you don't get the exact root cause immediately. So you will have to, if this is not the cause, it could be something else. It could not be due to some unclocked access or due to some register reads. The issue could be something else. So, but this is one of the debug mechanisms which we have, and we found it's very useful actually. And this was one of the first projects which I worked on when I joined Qualcomm, and which I wanted to upstream. So basically, I work in upstream team in Bangalore. So we mostly work on Chrome projects. So for Android, we have a dedicated team in Qualcomm actually. It's called as Qualcomm Debug Subsystem Team, QDSS team, and for Chrome, they have me. So yeah. So there are some limitations of RTB. So just a few to categorize them. One is design and one is functional. These are just my categorization. It's not like they have to be categorized like this. So thinking of this, so RTB is like, they have been designed as a separate kernel driver. So it doesn't need to be a driver if kernel already has some interface to have something like this, right? So kernel already has an interface or a framework called as trace points. So I think most of you are familiar with this, trace points and trace events. So we can, register reads or writes, we can consider it as just in some events. And then store them into the trace buffer and somehow get it out. So that is one thing. So you don't need a separate driver, and that too in kernel trace, where to have such a debug facility. So when I posted my first version, that was an RFC, the Ftrace maintainer, Stephen Rosted. So he gave me an example for x86 actually. So how they trace the register reads and writes in x86. So they read and write that MSR, it is something called as model specific registers, some control registers in x86. So they can read and write, and they can be traced. So using the trace points and trace events. So on the next version, I modified my code for using them instead of having a driver, complete different driver. So that was one thing. The other thing is about storing the RTB logs. So how do you store the RTB logs? So currently in downstream, we heavily depend on something called as RAM dumps. I think it's like core dump or something else, or in other companies or anything. So basically, we have a huge RAM dump size of memory, and then we take the logs out of it. So that is one thing where we developers find it like really cumbersome to deal with. We don't want to have a full RAM dump just to take care of some trace events. So that is one more design limitations. And functional wise, I would say like it would trace all register reads and writes. So if you take some serial driver, and you see the register reads and writes, it would be like a lengthy list of all the register reads and writes. So it doesn't have a proper filtering mechanism, I would say. So what they would come up with filter is, you could either trace only register reads and writes, or you could trace only the context IDs or IRQs. So that's what I mean when I say filtering mainly based on log types rather than the log contents. And for no log APIs, so there are something called as, there are functions like readle, writle, and raw readle, raw writle. So how do they filter out, if they don't want to log anything? So they would rename it as readle _ no log, and the other ones like readle, read B, read W, readle, read Q, and rename them. So there are like duplicate definitions right there, like duplicate definitions. And they, when RTB is not enabled, they would use these APIs, and when RTB is enabled, they would use the normal ones, where they would add some static trace point, not trace point, just a hook in the, which is called from the driver, from the RTB driver. So that hook might be called something like, log this read, log this write. So these are all manually added, and it doesn't provide actual filtering, good filtering capability. So that's why we had something called as trace points. So this definition is like, so what trace point is from Linux kernel documentation, it just provides one capability for you to add a static trace point anywhere in the important path. So your code or your driver or your subsystem might have some important thing to be traced or to be, or to be collected. You want some important information to be collected, and that's where you can use something called as trace points. So going to the definition, it doesn't make, you can go through the definitions, but let's come to two main points. So one is trace point. What does these trace points have? So one thing is trace point definition, and the other thing is the trace point statement. So I'll give you an example here. So this is one example for trace point definition and the trace point statement. So let's just look at this one. So definition, you can see there are prototype, arguments, then structure, then assigning, and the print case, and then define event. So basically what that declare event class means is that, it's a template. So now both IO read or IO write, or any register read or any register write, they have some common parameters, right? So you don't need to define two events separately. So if there is no declare event class, you can always have something like trace event, IO read, IO trace read, and down again trace event, IO write, like these things. Instead of that, we have some common parameters. So we can just define a template like this, where both IO read and IO write events can just use that template, and then can use them later on. And it's just about saving some space, saving some bytes of memory in order to do that. So main thing to notice here is what are the fields which we are going to print or which we are going to use. So mainly the log type, the CPU, the timestamp, some extra data from that, and then the caller. So these are some of the parameters which we are interested in. So coming to trace point statement, if we look down there, so you can look down there at do trace IO write. So you can see trace underscore IO underscore write. So that is a trace point statement. So that is something we are going to use in our code, where you want some register reads or some register writes to be traced actually. And so that return underscore IP, whatever you're seeing, it's just the built-in return address of 0, which is basically the caller information. You get the address, and if you print via, %PS, you get the name. So that is one thing. And the interesting thing here is the IO trace point active. So if you see the first line over there on the right-hand side, so there is something called the IO trace point active, and it's defined as static key false. Yeah. So that is something which, very compiler dependent. There is something called as jump label. If you have not seen you guys use dynamic debug. I don't know how many of you know about dynamic debug, but you usually see PR debug statements and dev debug statements, right? So, but most of the internal things and how it works. So one of the main things in there is that jump label. So that is basically an unconditional branching. So something like a go-to statement, which compiler supports. So GCC supports that. Clang, I think after 8, they started supporting it. So it helps in, faster execution, and you don't need a check to see. It's since it's an unconditional branch, you don't have the overhead of that checking if the branch should be taken or not. So that is one of the important things there. And the macros are just, the magic there. It's just about calling with stringify, so that I get to know what different log types are there. And so if you have any doubts in any of this, you can just ask me now. Yeah. You want to?
I have a couple of questions.
Yeah, sure.
So one thing, I'm from the scheduler team. one thing what will be super useful is once a device has crashed,
Right.
can we get the normal traces that we have turned on through the RAM dumps?
What kind of traces? That's
everything, like all the traces. In fact, parsing the entire ring buffer.
Right.
For every CPU. Have you guys looked into that?
Actually, we have an idea at the end of the slide with future ideas. I have something called as device RAM oops. So device RAM oops is basically you choose what you need to be traced, and we provide an interface where, on the next boot, you have all those logs. So it's the client driver responsibility to expose some information which you find it very useful. So printing the full ring buffer as such, like, what are the information you're looking there? Like, you can't just have everything just dumped there, right? That's what random already does it, right?
Oh, not quite. Well, random.
Yeah, you're talking about Ftrace data?
Yeah.
Oh, okay. Yeah. That is exactly one of the future ideas which you're going to say.
You have that in the future plan.
Yeah,
okay.
that is it. Yeah, that is the main one. Yeah.
Right now, my limitation right now is the ring buffers are all compressed, right? They're not presented in a string format.
Yeah, right.
So it's very hard to post-process them.
Right.
So if you have a plan to do that.
Yeah. That is why I'll say that. One of the future ideas is, porting all the Ftrace to use Pstore pages. So not as a part of random again. We don't want anything in randoms. So since, all the developer community here, so we want some simple interface where, after the reboot, I can just catch some sys interface and see all the logs, all the Ftrace logs I'm seeing. It's not just any specific trace events like, these reads and writes, any Ftrace data. So that is one of the future plans we have.
For the previous boot, you mean?
Yeah, for the previous boot, yeah.
Okay.
So I'll explain the Pstore concept again. So what is Pstore and how it can help in, instead of randoms, how we can use it.
Okay.
Yeah, it's a simple interface, way better than, not way better, I could say, but better interface than random, at least if you want to quickly, debug something. Okay. Yeah, I'll go through that, yeah.
I have a question about so that if there is already have some option which the dumps that Ftrace trace event, all the logs when oops happened, so that on the console.
Yeah, that you mean Ftrace on oops or something, right? Ftrace dump, basically.
Yep.
Yeah. That is there, but you can't always rely on console. That is what I'm going to say. There are several locking constraints. So a memory, like a trace buffer, is very fast, like Ftrace, right? So something in the memory is more reliable than what you see on the console. So that is what we feel. So although console, if you say the kernel is going to die, and it's not, we don't say it's very reliable. That's the only thing, right? Like that's why Pstore was introduced in the first place. You must be aware of Pstore, RAM oops, where, in case of any oops or any panic, we store the oops log in the Pstore. So we have seen cases where, console, we don't see anything.
So that you mean that the console drivers or something like that can be broke?
Yeah.
Okay.
Yeah.
Yep.
Console is always, there are several locking constraints mainly. So
because it can be very far your console, right? It's asynchronous by nature. Yeah. Whereas if you write to RAM, it's synchronous. So you're guaranteed to get everything before the crash.
Yeah, just before the crash.
I think that one point is that actually, I think you need to clarify. You are debugging the crash issue. Is that is the color panic or just the hardware lockup issue? I mean that if the hardware lockup issue, that means that the CPU have no chance to flash the cache to the DDR, or it also have no chance to dump the color panic. So for that case, that we cannot rely on the console anymore or the Ftrace, because Ftrace also use the cacheable the buffer.
Yeah, but in that case, we cannot, get the information in the cache. Yeah, even using the
Pstore, you mean, right? Yeah.
Pstore.
So even on our socks, right? So flushing of caches is taken care by a trust zone, TZ, something like a PCU sequencer, or some hardware takes care of flushing the caches. So actually, this RTB, the main reason for using uncached buffer, where that older socks didn't support such kind of features. We didn't take care of caching the flushes. That would actually create some more problems, and that was the reason why we use uncached buffer in RTB. But nowadays, the hardware takes care of flushing caches on the power down path as well as the power up path. Not power up path, power down path mainly. So for Pstore, it wouldn't matter, like, cache or uncached, it wouldn't matter much for us. So yeah, for CPU hard lockups and other things, console, we don't rely much on that. Instead, Pstore, we kind of, yeah. So if there are no more questions, I can go for. Yeah, so these are some normal ways how do you take trace events. So one is from command line, kernel command line. In kernel command line, you can just specify trace event equal to IO, so which will activate both the read and as well as the write, and you can trace both events. And after boot, if you want to trace specific IO read or you want to trace IO write, you can specify them, and this is how it looks. So this is not RTB. This is the this one upstream way of handling the register reads and writes. So this is just an example. It's not a crash example. I'll show you guys. So again, advantages of trace events. So this is not just advantages of IO trace events. It's in general trace events. So if you take, there are lots of ways of filtering. There is a subsystem filtering, and what I mean by kernel subsystem is, I have one more slide which I'm not here. So I compare driver subsystems and I compare kernel subsystems. So Ftrace is a generic tracing interface. So we don't have any very driver specific subsystems or driver specific tracings. So we mainly deal with Ftrace has all the kernel subsystems like scheduler, memory management, and some tracing, other tracing also. And it has various kernel subsystems, whatever comes under kernel / something, right? So Ftrace can trace all those data. But currently, for driver subsystems, we don't have much Ftrace tracing capabilities. Although we do have some trace events, we can add it to the drivers, but not that much. But the main thing we are interested in that, like SOC vendors, mostly we are interested in debugging some drivers or some other like GPU or USB or remote proc, or we are interested in knowing its state. So that is where we want to filter out. So Ftrace already supports filtering based on function name, wildcards, and as such. So yeah, so I'll go into that again. So again, for using IO trace point, why we use trace events. Again, this is the same point. Like we get all the features of Ftrace, so it's better to have, instead of a RTB driver, we can use IO events or any trace events. So basically, what I'm saying is, in future, it's better to have some trace events rather than having a separate driver out there for such functionalities. Yeah. So this is the main part. So downstream, so main use case is to debug abnormal resets. So downstream in Qualcomm or in other companies, we have something called RAM dumps. So we collect the full snapshot of the RAM memory, and then we start extracting them. But what if a normal kernel developer like outside Qualcomm or like us, or our Dragon board 410C boards with them, some 96 board developer wants to debug something. So they could have RAM dumps again, but the extraction part is quite harder. So we use JTAG, but we also use something called as random parser. But again, those are not feasible, and they're out of kernel tree, maintained out of kernel tree, and it might not be, tomorrow it might not be maintained as such. So it's better, what other mechanisms do we have in kernel where we can see those logs? So one main framework which is available is Pstore. So what is Pstore, right? So Pstore is nothing but a persistent storage. So that statement is not mine. It's from one of the articles which I was reading when going through Pstore. So it's a persistent storage for a kernel's dying breath, or in other words, it's basically an interface to capture kernel records. So initially you could say it was only for panics or oops, but now it's basically for kernel records, any kernel records, I would mean. And that will persist across reboots. So how it will persist across reboots? So Pstore has one main limitation, my main requirement, that it should be a warm reset. The SOC should support warm reset. So again, as most of you know what warm reset is, but I'll just go through that. So warm reset is simply a reset in which DDR contents are retained. And a cold reset is something in which DDR contents are wiped off. So you don't have any logs retained in DDR if there is a cold reset, and in case of warm reset, you have the DDR contents retained. So that is one of the main requirements for Pstore, and most of the software vendors, Android or Chrome, it's the main requirement from Google that you should support warm reset. So that's we already have. So we have that. Pstore is quite useful now. And different types of already supported records are dmessage, console, ftrace, and pmessage. So main confusion would be dmessage and console. So they both are same, right? So but no, actually in case of Pstore, dmessage logs will only show up if there is kernel oops or some panic. So only then it will show up. But console is not like that. So if you can enable console RAM oops, you are going to see all the console every time. But dmessage is only if there is some oops or if there is some panic. So that is the main difference between dmessage and console. And it's very easy to add another record interface. So like event trace. So what I did, I just saw, okay, how those are there and how it can be implemented. It's very simple. So you can just add your own records. If you have some more good information which you want to expose, you can just add it there. It supports it. So yeah. So event record edition was one of the things as a part of this project or this feature. Then comes the backend. So Pstore is a front end, as in it's an interface for files. It's a file system basically, giving you some data. I mean, giving an interface for you. But what happens in the backend? So where do you store that data? It's basically in RAM. So RAM is something. RAM is a backend here. So RAM oops is basically, the name is RAM oops mainly because initially I think it's mainly was used for debugging oops or any panics. But finally, now I think they are using it for all other things like all other records, not just oops or not just panic. So better definition from my side would be it's a backend interface which enables Pstore records to use persistent RAM, which will persist across reboots, which will survive across reboots. So the records, these are the formats of the records which you will see after the reboot in sys fs Pstore. So that I think I'll show you guys. Yeah. Okay. Yeah, these 4 things you can see in cat sysfs Pstore. If you do, once a Pstore is mounted, you can see these records after the reboot. Sorry. And how do you add this support? So it's a DT based approach. I mean, you can just add a DT node in your device tree. This is an example for Dragon Board 410 added by Beyond actually. So he just took the last MB of RAM and used it as a reserved region. I mean, he just carved out some reserved region and named it as RAM oops. So you can use that unless you're going to use that last MB of RAM for something else. So you can easily define a node like this and you can just say, okay, this is the record size. This is for dmessage. This is for the console. This is for the ftrace. And this is the total size. So actually this can't be more than that. So, so these should be equally divided. So these are how you define a RAM oops node in the device tree, and some optional parameters, optional properties, as well as required properties are there. So it supports ECC as well. So there is some error correction.
I have a question. So that the Pstore is storing that on memory or just a flash? Let's say.
It's storing in RAM.
Storing in RAM.
Yeah.
Okay. Yeah.
So Pstore is a front end. So there are 2 things here. One is Pstore, which is a file system. That's it. And there is a backend. Where do you store that data? RAM oops is something where ARM systems usually we use RAM. But I've seen in x86 there is something called as, you can basically use any non-volatile storage which you have access to.
Yeah. Usually the x86 servers has a Pstore flash backend, but that is very slow.
Yeah. So there is something called as ERST table or something. So basically any non-volatile memory, if you have access, you can basically store the data over there. So it's like that. So it's a
This memory is carved out already.
Yeah.
So is it?
No. You have to.
Or does it get carved out when there is a crash?
No. It's initial during boot itself. When Pstore gets initialized, it's mostly, I think it's a post-core init call, like quite early, very early. Yeah, very early. before the driver gets initialized, any of the drivers.
I see. And it stays resident in the memory, is it?
Yeah, yeah.
Or
As in, like,
so once you reboot, right, you'll go through all the bootloader stages. And it is expected that the bootloader should not overwrite or corrupt this
no,
usage.
It won't do that. These are the kernel memory. Bootloader won't bootloader won't
Mess around
touch
with
it, mess around with. So main thing is the cold and the warm reset part. You know.
Might be tangential, but how can the bootloader not mess around with that memory? I mean, if it writes to memory, maybe that just happens to be a Pstore page, right?
Right. So this
What
is
guarantees that it won't stomp on what has been recorded, the bootloader?
basically, the DDR memory is not something to be messed around with by any of the bootloaders, right? I mean, I don't see anywhere where a bootloader requires some access to the DDR.
When you say DDR, it's just RAM, right? It's,
Yeah, right.
So the bootloader writes to RAM to load the kernel and boot. Or,
yeah,
you know,
at a specific
EFI will write
location.
to RAM, you know, a lot of
Yeah.
things write to RAM
Right,
during boot.
but at a fixed location. Even the kernel is loaded at a fixed location, so it doesn't touch other location. I mean other memories.
Okay.
So even the kernel, which the final loader, maybe ABL, Android bootloader, there are fixed locations.
It doesn't mean anything.
Maybe there is an honor system at play here where the bootloader is requested not to muck around with this area.
We don't do that anything kernel specifically.
Correct.
Yeah, bootloader shouldn't be doing that.
Because this is warm reset, right? It is like you have regions, only part of that would be, this is carved out during your cold reset. And it stays that way, right? Unless it's another cold reset where it's going to take out everything and start writing. Warm reset will only muck around with some places, not everything.
Okay.
Yeah, it's
I
just
disagree
the
with that.
reset.
But
Yeah, I think it's just the different kinds of resets which do things differently. And if you've already carved out, it's not.
Because the reset have the
Yeah, it won't. But then bootloader also will behave differently when it's warm reset, I think, right? Yeah, so it won't do like how it would do during a cold reset. And that's the reason it will still persist through everything.
I guess what I'm saying is that I don't believe that the bootloader will not, accidentally stomp on what has been recorded, unless, the bootloader is aware of all that Pstore
Yes,
thing, and
it is.
there's a protocol that says, hey, don't write higher than the 32 30-second megabyte in memory, or something like that, right? But there has to be some kind of convention.
Yeah, so warm reset the bootloader handles it differently than what it would handle a cold reset. So then there are areas that it won't touch.
Okay, but it's not just the bootloader, right? It's EFI, it's all your drivers that get loaded by
even
EFI,
cache,
and
like everything, like you're during warm reset, you're not losing your DDR state, right? We have like abnormal.
I understand
reset.
that.
Yes, so then. Yeah,
so there is a page in memory that keeps the state. I get
Yeah.
that, right? But what I don't get is how you prevent everybody who writes to memory from writing there, because they don't know where there is.
Right. One way, what I can say is, I don't know for Android, but for Chrome, bootloader is aware of the RAM oops region actually, because in Chrome we have different stages of core boot. So you have RAM stage, ROM stage, depth charge, and before that there's something called as core boot tables. So actually Google, at least who work on the bootloader side, they specify. I mean, for Chrome we don't specify the RAM oops node, which I specified, right? So it is coming from the depth charge, the bootloader itself. So they exactly know which region to be reserved for the RAM oops.
Okay.
So for it,
passes that to the
yeah.
And when you reboot, you assume it's the same
Yeah.
bootloader, so it knows.
Yeah, so it knows. That is true in Chrome, but for Android, I'm not very sure how it's going to work.
And the other thing is, if you keep track, if you have an understanding of the application that you're running, like you probably wouldn't do this on a device in the field, but if you have an understanding of the applications that you're running, it's very easy to determine if you're going to hit certain addresses during the boot process and just avoid those. So it's a little bit of just understanding it. Most of the stuff that I've seen that turns this on by default, they put it way out on the far side of memory so that doesn't happen.
Yeah, this is actually the last MB of RAM.
Yeah.
So that's something which is not usually touched. So the choosing of that, should be taken care of by the bootloaders or after going over the memory map properly. So, okay. So while going through this, actually what I found was, why only one event I want to store in Pstore? Why only the IO trace events? Why not all the trace events can't be stored in Pstore, right? All the trace events. So that's when we thought, okay, we'll go for that. And we were able to do that, and this is one sample where shed trace event was being captured to Pstore. And it looks very quite useful, you know. This is the last entry from the, just before the reboot. After the reboot, this is how we mount Pstore. And if you see the Pstore, Pstore contents, and the last one, it basically shows you the next the next actual process which is running, that is reboot command. So this is quite useful, you know. So we found that, okay, why not just add all the trace events to Pstore? It's very useful. So that's what we did. So we added all the IO trace events to Pstore. Not IO, sorry, all the trace events. So again, this is one of the main things where I felt like Ftrace has one small limitation. So we can't filter based on the file names. So this is something I've been seeing in Ftrace, that I can't trace by saying, okay, file, I want to trace only USB, driver/USB/star. So that is not something which Ftrace has. It can trace it has all types of filtering mechanisms, you know, by names, by expressions, by wildcards, but not this one. So that is where I was trying to find out, okay, what other filtering mechanisms do we have? So that's where I found, okay, there is something called as dynamic debug. So dynamic debug actually provides way, to filter traces based on the file names, based on the module name, based on the expressions. So it basically covers the most important parts which we need. So that's why we thought, okay, why not try dynamic debug? So if folks who are not aware of dynamic debug, so basically you would post some drivers out there, and the maintainer would say, okay, change your PR info and PR debug statement, info or dev info statements into PR debug statements. So that is basically, because they can be dynamically enabled and disabled at runtime. So you don't want any overhead. It's not like, dev info or PR info or print K with the kern info flag, where it always prints to console, You can basically enable and disable at runtime. So that's what dynamic debug provides. So how do I use it for these trace events? So this was something new actually, we use normally print statements like PR debug or dev debug in some drivers, and we just a line, it's just a line. And we see, okay, it can be enabled or disabled dynamically. But how do I add it to, for these trace events? So it turned out that it was very simple, So basically, I'll give you a brief explanation how the dynamic debug works. So if you see the sections, so basically dynamic debug, it just creates a section of all the, based on the flags you pass. I'll explain you in a bit actually. So this is what it is. So a sample of how dynamic debug can be used in kernel. That is a kernel command line. As a kernel command line parameter, if you want to use dynamic debug, then you use it that way. So file drivers sock ucom star. So that's not something what Ftrace provides you, right? And +C is a flag which I added for events. So there are +P for print statements, and there are lots of other statements. And again, it seems that double quotes is very important for the kernel command line. Otherwise, it gives some error. I have to see why is that. And after boot, it doesn't matter. Like you can just follow this step to actually, enable dynamic debug, and this is how it looks. Yeah. So it will, these are the reads and writes which are enabled dynamically. Now, if you enable, I'll show you at the end of the slide actually how it's used actually. These are the events which are enabled, and if you see the cat syskernel debug trace, you could see all these events being traced. If it is being traced, you could see those events. So, this is the sample one. So here, the first step is to provide the kernel command line, or after boot you can provide it. So I want to trace driver sock ucom, all the reads and writes happening in driver sock ucom. The first one, the dynamic debug, dyn-dbg, file driver sock ucom, trace event, tp pstore. Okay. So basically, the TP Pstore thing is to specify that these events are going into Pstore. And trace event equal to IO is for IO trace events. And this is for specifying the filters. And yeah, this is a sample program which I've written the same way, the first one. Like, on reading that file or reading that register, we would just crash the boot. So after restart, I mount the Pstore and I find that event. And I see exactly which read caused the issue. So this is already known. I mean, I knew that, okay, that is a sample program which I created to cause a crash. That is true. And what I did was, I placed this sample crash program in driver sock-qcom. Okay, so whatever the file is there in driver sock-qcom, and whatever the reads and writes are there in driver sock-qcom are being traced now. So once I read that register, secure register, it crashed. And all the events from the driver sock-qcom is getting traced. And it's, these are some of the events which, events in the sense reads and writes. So these are the events which happen. And I can see easily that, okay, that is a place where it's getting hanged. And you can just use GDB or whatever other mechanisms you have to easily find which is the exact line causing the issue. So this is something like, raw readle, I'm reading that at that offset, it's causing the crash. It's that simple. So mainly here the takeaway is the usage of filtering mechanism, that is dynamic debug. Yeah, the future ideas what Bijit I think asked. So yeah, so when I had an idea like, okay, why not bring all the trace events to Pstore? I think Joel had an idea where why not bring all the Ftrace to Pstore? There are lots of, Ftrace has a lot of other tracing mechanisms as well, like a graph tracer, a latency tracer, and a lot of other stuff. So here it's not about getting Ftrace into Pstore, but rather getting Pstore, using Pstore pages for Ftrace, and getting all those extra Ftrace functionalities which we have in Pstore. So basically, as I already said, Pstore, what it provides you an interface where you can weave the logs of the previous boot. Ftrace has all the features which you want to be tracing. And when they combine, actually it makes a lot of sense because you will have all the trace data as what he said. He wants whatever is in the ring buffer to be available to him, right, after a reset. So that's what it's going to be used, Ftrace using Pstore storage. Now that idea, I think, yeah, it has been selected for Outreach project now. So Joel and I will be co-mentoring that project. So for this, I think till March 2020. So that was Joel's idea actually. Yeah. So that is one of the ideas. And device RAM oops, yeah. This was one of the ideas which just flashed me by when I was working on one of the internal debug drivers, which I was trying to upstream. So if you have some client driver, like say USB or any remote proc or some GPU, and you have some information which you know that it's going to be very useful for me in case of some crash. So why not provide an API and export that from Pstore so that client driver data or client driver can use that and store that information. You already have a Pstore interface, so why not use that? You can get it. You can get your useful information on the next reset. Like say you are debugging something and you know that okay, this is the area which I'm going to see because this is the culprit, or you have some intuition that okay, this area I need to debug and then I'll find some information, and you already have some data which you think is very important. Why not just put it to Pstore? It's very good for post-mortem debugging actually. So I was checking for CoreSite also. Can we bring it to Pstore? But yeah, it needs some work actually. So yeah. So this is one more idea which I'll be working on, and one more Ftrace idea actually. So I was thinking, why not Ftrace can have filtering based on file names, module names. Can we use something like dynamic debug for Ftrace? But one disadvantage with dynamic debug is the size would increase dramatically. So that is main disadvantage. Yeah. So we might be able to find something to get around that, and it's very useful. I would say, file-based filtering. Like I want to trace only USB subsystem, and I want to trace only GPU. I want to trace only UFS or any other subsystems. It's pretty useful. So I have that in mind as well. So yeah, so that is one of the, one more idea which I'm going to work on. Yeah, so if you have any questions.
Okay, I have Masami Hiramatsu, the Ftrace, one of the Ftrace reviewer, and I have several comments on the ideas. Could you go back to one feature? So that's the first one. How do you? I'm not so sure about how Pstore stores the data, but for storing data into the Pstore, it seems that the Ftrace function trace storing on the Pstore is a bit different from the original Ftrace, so that they make a different interface.
Yeah, very true, actually.
Yeah. So I have two ideas for implementing this on the Pstore. One is to allocate the memory, Ftrace buffer memory from Pstore memory, but that is not good work with the Pstore LAMOOPS interface.
Yeah.
So that's another idea is to add action to trigger. Each event has a trigger action interface.
Okay, yeah, right.
So that we can add some Pstore command on that.
Okay.
So that then Pstore handler called via each event, and the event write the event data into send the event data to Pstore.
Okay.
It will clone the data. But I think
But it's only for events, right? Not the complete Ftrace. I mean here complete, even the graph tracer, the tracer infrastructure itself. I'm not talking about only trace events.
Yeah, but at first we'd better to start from the event. Support. Because that Ftrace and the Fgraph tracer is a bit different.
Right.
Yeah.
I'll add you to that mailing list, maybe Joel, and we can discuss.
Yeah.
Very true. Yeah.
And also the file-based filtering. It could. I don't like to mix it up with dynamic debug interface. We'd better to add some other interface, independent interface on the trace surface. Because that's we will introduce some capability for tracing. And that will allow user to access that trace surface.
Right.
So that is one usability issue if you mix it up. So that's
I was just saying, can we do something similar to dynamic debug?
Dynamic debug is actually based on the jump label, but with some static key.
Right.
So that we can make another static key database for the I/O event or something like that, so that we can filter it out on one independent special file.
I also had one more thing where GCC already had something called the F instrument functions, if you're aware. I had this question. Maybe I should have asked you or Stephen. Why that was not chosen and used? Why PG was used instead of this one? Because this provided it had file-based filtering mechanisms. It had, to add instrumentation to both the tail of the function as well as the head. So to both interfaces. So I always had the doubt that why that was not chosen.
I'm not so sure, but I think that is because the function at first. Stephen started to implement Ftrace. There is only the mcount interface, so that we just use that. And maybe we can also make a user space tool to make generate a filter. Function name filter based on the file name.
That seems better than having in kernel. Something like that. Thanks.
So since Pstore has a major disadvantage of following disallowing cold reset, right? So can we store the data into some non-volatile data memory instead of RAM?
It's a possibility. Yeah, it's already being done in x86 case.
Okay.
But you would have to write the backend driver.
Sure. Yeah.
Yeah, RAM oops.
Because in some SOC, I mean, we cannot just do a warm reset.
Yeah, actually there was a recent work by someone from one of the All-Winner Tech, I think, where they would use disks, some disk like USB or UFS, I think, to store Pstore data. Yeah, that was a pretty great idea actually. Even for us, I was trying to go through that. Yeah, something like that would be very useful.
Yeah, at least we can give an option to store to different locations.
That is already.
Then we can get around with the warm reset problem.
Yeah. That is one of the things. Yeah.
Did you internally have some evolution to compare between use the Pstore and use the Corset, the STM? Because I think essentially that you want to let the trace data can be output to the DDR, not impacted by the cache.
Right.
So you can use the Pstore.
Right.
The Ftrace based on the Pstore.
Right.
And the Ftrace also can based on the, for example, STM.
Right.
The STM can output to the DDR.
If it's in DDR, then it's almost like very easy to get it out of Pstore. So I think we can get the STM data out of Pstore, but it's in some other format, right? It's not readable format.
Yeah.
It has to be formatted to either text or something when reading. That is doable. That is quite doable. But
You mean the? But even I have overhead for the STM, and even there I have overflow. But I think it's not a big deal, right? Because that we don't care about the lost data, we just care about the NAST, the trace data.
yeah, because one more thing, Pstore you would have to carve out so much region again if you want the STM data to be exported to Pstore. So that is one of the things. Usually we keep Pstore to very minimal, right? Because it's used in production actually.
I think that the STM have less overhead than the Pstore because the Pstore you will to the data will output to the DDR, but the STM you will output the compressed the trace data to the DDR. This is my personal.
You add the trace header, right? You add a trace header for the STM B2 packet, right? A good thing about using STM is to correlate with other pieces of data, right? Other than Linux kernel, maybe some other processor because of the universal timestamp. I think that would be a good thing. But then STM has to add the headers, right? That's the overhead. And we have to go through the ARM formatter frame as well. That's another overhead.
Yeah.
But this is raw data, right? We store the raw data in the DDR. Yeah. So that is smaller space, but I mean, there's a trade-off between those two.
So these are actually being currently used internally as well. Chromebooks. They are active actually. So, yeah.
There might be a problem also if you want to put both types of data in the same buffer, both, your tracing facility and then the hardware, the core site, right?
Yeah,
because the hardware will take precedence, right? The hardware doesn't know what your software is doing, right? So you can't prevent the hardware from writing in a buffer when it wants to.
Yeah, but we do take care of partitioning clearly in case of, we partition now into console or dmessage or ftrace. Clearly, right?
Okay, so you already have separate buffers, but then you can't correlate events anymore. Do you have a timestamp, a universal one?
No, we don't have any timestamp.
So you can't correlate, right?
No.
Between different traces?
We can't correlate because we don't need to do that for console message and an ftrace, right? Console is something different and ftrace is something different.
Okay.
But within ftrace, we have timestamps.
Okay.
And we can correlate only ftrace. And we can only see console. So that's how it's separated out. So if you take core site, maybe it's a core site, we specify the core site size and a separate buffer for core site. And in core site, we have a timestamp.
Yes, okay. And then you can correlate, okay.
That way we can do.
Of course, you can correlate different processor. Like
Again, we would again have to partition it into per CPU cores.
Not necessarily. You use the same buffer from core side.
Okay, you mean to via timestamps?
Yeah, using
that is
timestamp.
also.
Yeah. Then you have a universal timestamp to correlate every single CPUs or processors.
Yeah, maybe we can make a Pstore backend core side driver.
Yeah, I mean that's
Yeah.
the options, right? You can do DDR, you can do file systems, and then core side.
So, I work for VMware, and I'm wondering if there's another backend that you could use for your tracing work, not just Pstore, but also, I mean, you mentioned that you don't want to use the console because it can be unreliable, right? But making a hypercall to the hypervisor is reliable and it's synchronous, right? And it's fast. So this is something you could consider, like extending one of those hypervisor methods, so that every single hypervisor can implement, what is the right thing to do, what is the right hypercall to do to just log that information somewhere, typically in the virtual machines log.
I haven't worked that closely with hypervisors, but we can maybe.
That would be. Yeah, well, that's the only idea, right, that I have is consider a different backend, and because this is debugging. Is a very good fit for virtual machines, right? Because you can reproduce, you can run again. It's easy, right? So unless your problem is very specific to some hardware, if it's a software problem that you're debugging, it works well in a virtual machine.
Yeah, that's true.
With your use case, then it makes sense to trace it through core side. Then you can have multiple software writing to the hardware and then spitting out the traces without worrying about different threads, different execution environment, that kind of stuff.
Yeah, that is true. We can have some backend driver.
Another thing that I was thinking about as you were describing your project is also the ability to tell the hypervisor of where you put the data, where is your RTB, right, in memory, because then you don't need to reboot, right? You can just the virtual machine crashes, and the hypervisor or the application that represents the VM, Linux or wherever, can just give you the dump, right?
Yeah, right. But for our use case, Chrome didn't have any hypervisors, so we didn't look over those use cases. And even Android, we don't have a live hypervisor. Like we have a backend hypervisor in Android, but we don't have a hypervisor like KB. I mean. Which is interactive, Yeah, it's only for security purpose.
Because I know we already do that. For example, macOS and I think Linux, when they crash and they use EFI, they write to the EFI and VRAM. They write data for the next reboot to decode, right? And we detect those writes in VMware. And so when that happens, we can show you the oops or the problem before even you reboot the VM, right? It's very convenient.
Yeah, that is true.
In EFI and VRAM is typically 64K, 128K. So it's not, you mentioned non-volatile RAM earlier, but I think you were referring to NVMe and so unlimited amounts, right? Yeah.
Why don't we make our BART.io Pstore to so that the sender the Pstore image data directly to host. And host stores, or on a leaking buffer or something like that. That will be better. Yeah.
I guess that's what I was referring to when I said, different backend for Pstore and make an hypercall. But I think, that's the same idea.
Yeah. Keys would be very happy to have such ideas actually. Keyscope is a maintainer of Pstore. And we can work together. Yeah. Feel free to send. Contact me or anything, we can go over this. Sure. Yeah. Any questions?
That was interesting presentation and good work. So thank you. From just a few notes from my experience, tracing was good in production if it's very small overhead for whole system, right? In your case, it looks like you store the data to different format for Pstore area, so you just transform data and collect it in one place and probably use some compression on it. So you slow down the whole system. Our solution like that was, for example, LTT, how it works. So if system crashes, key dump reboots system to new kernel, and you just take trace buffers from previous kernel, and after that you can save and analyze. And speed is more fast because there is separate ring buffer for each kernel, and traces go directly there.
The trace would be on, right?
Yeah.
You would be continuously adding something to trace buffer.
Yeah.
So here, let's say if we override that part, we don't put it to trace buffer, and we just put it to Pstore, then it would be the same thing, right? Like we don't put it to trace buffer, let it go to only Pstore buffer.
Well, it depends. What I look for LTT code, they just optimize ring buffer for trace, so it's not a Pstore RAM. Or if you consider Pstore as just place of the RAM, and internal representation will be the same buffer, which is optimized to collect all tracing data. It's one deal. If you just use Pstore as a text file, then it's the other case.
That was one of the future ideas, using Pstore pages for Ftrace. So basically there won't be anything like trace buffer. So basically we'll be directly writing to Pstore, either in raw format or...
Here I think should note one thing is that if you use the color panic, that means that every CPU have a chance to get a notification. So the CPU can be flash the cache to the DDR. So for this case, for example, we can use the curl dump to capture all the DDR, the content. Then we can save this content. For example, use the Red Hat the tool crash to extract the Ftrace the buffer and all the Ftrace related event format, so can do the post analysis. But for this case, if we want to use the Pstore, usually that means that the system is not panic, it's just hung. So like for example, the bus lookup, or they have the hung issue. For this case, that the CPU have no chance to handle the panic notification.
So you just reboot watchdog and take, right?
So this is why it must to use the Ftrace to connect to the, for example, Pstore or other hardware mechanism to directly to output the trace data to the DDR. So in this case, that we can avoid the data, trace data to store in the cache. So this I think they have some different between.
Yeah, it's a little bit different use cases, but it's a very uncommon situation when your watchdog pre-timeout event, for example, cannot raise some watchdog action, and you cannot do panic event in the kernel. So
so actually, for the lookup, that it will need to rely on, for example, the watchdog, right? So to reset the SOC, but it will not to reset the DDR content. So in the DDR, there still because we have saved all the trace data directly to the DDR. So after the reset, we can get out the DDR, the content, but we cannot get out the trace data. Cannot get data from the cache. So this is why the Pstore introduced for this case. It's clear.
It's basically kind of same thing, right? Like say KDUM you're talking about, and basically it's same thing random case. Like you have all the trace events already enabled, it's being collected, and system crashes. You collect the random and you pass it. So, but here we exactly don't want that. We want a simple interface where I just want to reboot and I want to check like say IO events only. And I know that it's something to do with the USB driver crash, and I want to see, okay, I've already enabled the filters, and after reboot I'll just go and see, okay, sysfs Pstore that IO trace events.
Yeah, so that means that probably you will not turn on it on production system. You will do it for some debugging or
Okay,
some analyzing, right?
Initial stages, yes. It's very useful for bring-ups, which we go to where, suddenly USB crashes. But Google has some requirement for production as well.
Oh.
But yeah, I don't know what exact data they require. No, yeah. But at least that user space messages is widely used. It provides an interface like the P message which I was saying in Pstore. So user space can just write to that interface any data, and that would just get logged there. And on next reset, you see all the user space data right there in the Pstore. That is something very useful. So, yeah. Choosing of data is very important, I feel like. What data we want. So that comes in again device RAM moves as well. Like the client driver should be the owner who will choose, okay, I want only this data to be exposed, and I know that this data is going to be important. So that way, yes.
Yep.
Yeah, thank you. Thanks.